So good morning, everyone. It's a pleasure to introduce the first exercise.
Thank you, Jan. So always a pleasure to see you again. Maybe it's a little too loud, you know? I mean, we can maybe decrease a bit the sound. Anyway, so let me remind you of what we were doing. So, I spent 2 hours really explaining to you the whole theory of TFT. Maybe that was a little too long, I don't know, but maybe too detailed. You decide. Anyway, now we'll rather go to some more recent works. Maybe a little easier to state, I don't know. But let me remind you of what we are doing. So there was this ENV, which is the ground state energy, so that's the minimum of the spectrum of HNV, where HNV is the n-body Hamiltonian. For some interaction potential W. Like this. Okay, ground state energy in an external potential of V. We also had, if you remember, an En theta of V. That was the same, but with W equal to 0. In this case, you can just compute, and for fermions, you get the sum of the n first eigenvalues of minus Laplace plus V. That's for fermions. And for bosons, you get n times lambda 1. We're going to discuss essentially fermions from now on. And we maybe only discuss fermions, but most of the theory doesn't see whether they are fermions or bosons. And then we introduced 2 universal functionals which we are going to study today. So there was the f of rho, which is called the Lieb universal functional in DFT, and that's just the lowest kinetic plus interaction energy you can reach for all quantum states having density rho. So rho is given, okay, so that's the infimum. Actually, it's always a minimum, so let me write minimum. And it was very important to use mixed states and not general, not pure states. So minimum over all gamma with trace gamma equals 1, and rho gamma equals rho of the trace of Hn of 0 gamma. Okay. Minimum kinetic plus interaction energy under the constraint that the first marginal, if you like, is fixed. And I would like to insist that it's a little bit like a multi-marginal optimal transport problem, but quantum, so non-commutative, because you fix one marginal, and then you minimize something which is a little bit like a cost, but here it's a trace of some Hamiltonian. So if in the room there are people knowing optimal transport, I know there are some, then it's the quantum equivalent of a multi-marginal optimal transport problem. Very good. And then we also introduced the T of rho, which is the same where W is equal to 0. So the minimum of rho gammas, with rho gamma equal to rho, of the sum, the trace, sum j equal 1 to n of minus Laplace x j gamma. And of course, everywhere we assume that we either restrict to fermions or to bosons. And T of rho for bosons is completely trivial, so that's why we will not really discuss it for bosons. For fermions, we knew that we have an inequality. And we also have it for bosons, but for bosons it's just equal, because particles are just IID if you fix the density. Very good. So yesterday we explained that when we study these 2 functionals, then we need to assume that square root rho is in H1 of Rd, which we are going to assume now. And so finally, I'm now finishing my summary. So what's the main idea of TFT is to approximate these two functionals, replace them by simpler functionals to get a good approximation of E and of V. And there are really two ways. So there is orbital free DFT. So orbital free DFT is just writing that E and of V is the infimum over rho, okay, of f of rho plus rho v. And so that's an exact formula. Okay, and then in orbital free DFT, you replace this guy by an approximation. Okay, so replace f of rho by an approximation. For instance, if you are in dimension 3 and W is 1 over x, then the easiest approximation is the Thomas Fermi, which is the Thomas Fermi constant 4 to the 5 plus 1/2 the Coulomb integral. Rho of x, rho of y, divided by x minus 1. Dx dy. Okay, that's Thomas Fermi that Jan Philippe has been discussing a lot. Very good. Of course, it's way too easy if you want to make good predictions. And so then there is Kohn-Sham DFT. So Kohn-Sham DFT is different because you really want to think of a non-interacting problem. And the way to introduce the non-interacting problem was to write E and of V in a different way. Okay, so it was the infimum over gamma of the kinetic energy, so trace minus lambda x gamma plus V of x j. Gamma, okay, plus maybe I call it E dxc of rho gamma, like that, where E dxc of rho is just f of rho minus t of rho. Very easy. Okay, so it's a strange way of writing it, but that's really Kohn-Sham. So you have a non-interacting problem plus a non-linear term which only depends on the density. And so an example, if you decide, so dxc is for direct exchange and correlation. Okay, because you need to approximate all these terms, if you like. So what is the direct? So usually the direct term we write explicitly here. I did not. So the direct term is just 1/2 the double integral of w of x minus y over x over y. So which I can always put if I like and then subtract. That's the direct term. And then exchange is really the idea that an electron should not interact with itself. Okay. So that's one thing that you can take into account, and correlation is really describing correlations between particles. Okay. And so today I will discuss the local density approximation. Which is called LDA. Which is a regime in which both T and F simplify. Okay, and so that's it's actually the simplest approximation in DFT. Okay, and it's also what people call the mother of all approximations. So somehow all the models they start from the LDA, which they then complexify to get more accurate models. So that's the most famous approximation, and actually it's really due to Kohn-Sham. So they are the ones who suggested to use this approximation in 64, maybe 66, statistics are not so sure anymore. Except at the time when they tried to do calculations, it was not working very well because LDA is quite good, but it's not perfect. Okay, so it's really in the 90s where they could complexify these models that DFT really exploded. Any question concerning this analysis? That's so.
What is the main difference between ordinary and function? What type of formulation?
No, so here the variable is going to be your gamma. I'm going to explain very soon that you can of course express this using only the small gamma, so the one particular density matrix. And in chemistry, they actually assume that it's a Slater, okay, which is okay. And so you really have orbitals, right? Because you're optimizing over an operator. Okay? And here you don't have any orbitals, your variable is just rho. So that's the difference. Of course, you get the same result, but it's not the same to approximate f here, or to start from here and approximate f minus t. Which you see immediately, right? If you just do this naive approximation here. Okay, so if you use Thomas Fermi here, then you replace by this. Okay. If you do the same kind of approximation here, then there's no rho 5 third, right? Because you already have described the kinetic energy perfectly. And so you will, so here, if you do this kind of approximation, you end up with a reduced Hartree Fock. And if you think of Ian Phillips-Stokes, reduced Hartree Fock is already much better than Thomas Fermi. Okay, if you think of atoms, it gives already a few terms in the expansion. Okay, so of course, these manipulations are formal and they give the same answer. But once you start approximating F or the E here, then you somehow immediately get better models here. So orbital free DFT is not very popular because people have not found very good Fs so far. But they have found quite good E's. And so people use more concha. But it's a very, very important open problem to find good Fs, because then one could treat much, much larger molecules. Because it's much easier to have one function of 3 variables instead of n functions when n is large. So orbital free DFT is not working very well, but people would really like to better understand it. And I think they believe that using deep learning or something, they could learn or invent better functionals on that side. But so far it's not worked very well. Any other question? No, everybody's happy, or maybe unhappy. Anyway, so let me make a remark, which I quickly outline here concerning the one particle density matrix, which you've also seen in the talk of Ian Philip. Okay, so let me remind you that there is a small gamma, which for a wave function, so let me define it through its integral kernel. So it's n, and then I do a psi of x, x2, theta psi of y, x2, theta bar dx2, dxn. Okay, so it's a kind of marginal, but where you really see the quantum nature anyway. Now it's not a marginal in the sense of probabilities, because now you use that it's a square of the psi, so you put two different variables. Of course, if x is equal to y, you get rho. But this guy is really an operator, and of course, when you have a big gamma, which is a sum of gamma I, psi I, with the sum of gamma I is 1, so that's a mixed state, just a convex file of pure state. Then the corresponding little gamma is just the sum of the gamma I and the gamma of the psi I just by linearity. And so the question we ask is, so we make the remark, you see that when you compute the trace of minus Laplace xj sum j equal 1 to n of gamma, then actually you can express this using only the small gamma as the trace of minus Laplace gamma. So be careful here, it's a trace in the big n-body space, L2 of Rb to the n, symmetric or anti-symmetric. And here it's a trace in N2/RD. Okay, so it's very good. You are now in N2/RD. You don't see N anymore when you take the trace. And same for V, right? So when you compute the trace of the sum of the V of xj of the big gamma, and that's actually the trace of V gamma, which is also the integral of V times rho gamma. Good. And so the natural question that we need to understand is, what is the class? I'm sure you know the answer, but I want to clarify this. What is the class of gammas arising from mixed states of n particles? Right, because you see, the T, for instance, where T is here, and the T I can write as the minimum over all small gamma, so that the rho of gamma is rho, and the trace of minus Laplace gamma, and so I need to know what's the class of small gamma. Okay, and I'm sure you know the answer, but let me tell you. So this is, so for fermions, I'm only discussing fermions. Okay, so that's the class of self-adjoint operators which are between 0 and the identity in the sense of operators, so that the trace is n. Okay, that's for fermions. And so in particular, you conclude that the T of rho we can re-express fully using gamma. So you get the infimum, which actually is the minimum between all, for all gammas between 0 and 1, trace gamma equal to 1, rho gamma equal to rho gamma of x is just gamma of x of the trace of minus Laplace gamma tracing it to about t. So you see, we don't really see, n. Well, I mean, when rho gamma is rho, I don't have to specify this because integral rho is n. Okay. So now the T problem is a pure one-body problem. We don't really see anymore the n-body space. And it's the same for Conshan here, and that's what I was saying when I answered the question of Laszlo. Right, so here, instead of minimizing over the big gammas in the n-body space, you can now minimize over the small gamma in the one particle space, because this term here only depends on the small gamma, and this depends on rho. Okay, so maybe I write it because that's important. So you also deduce that the En of V is the infimum over all gammas rho of the trace of minus Laplace plus V gamma plus this E, D, X, C of rho gamma in Conshan, and the eigenfunctions of the small gamma are called the orbitals. Okay? Very good. So, how do you prove star? Do you know that? So the fact that you get all the operators between 0 and 1 of trace n for mixed states. Is it clear to everyone, or should I explain? Maybe I explain quickly. Cannot hurt. Yes? Yes, thank you. Then I have to put trace gamma is n. Thank you. So the proof of star, right? So let me tell you that understanding the set of gamma psi with the psi n-body state is actually complicated. Okay, that's a complicated question. We don't know what's the set. We know in some cases, but it's not so easy. Okay, and it's not this simple set. So when you look at pure states, the set of one particle density matrices is not so easy. For instance, if you have two particles, then gamma must have only degenerate eigenvalues of even multiplicities. I mean, which is not so easy. Anyway, but you see, when you look at big gammas, what you're doing is you're just looking at the convex set of those guys. Okay, so it's clear that the set of gamma arising from big gamma is convex. You can also show it's closed, say for the choice class. No. Okay, so it's a convex set, it's closed. Okay? That's the remark number one, just because when you look at mistakes, everything becomes linear, so it's easy, it's convex. And the second remark is that it's included in that set, maybe I call it K, Kn. Okay, so it's included in Kn. So for this you have to know, so the choice is n, that's obvious, that it's non-negative, it's obvious. And Jan Philippe told you, I mean, that gamma is less than 1, that's the Pauli principle for fermions, and it's not so easy to prove if you don't know second quantization, but anyway, so let me also, okay, so that's really the Pauli principle, so the fact that your fermions, so for bosons it's the same, but without this constraint. Okay, good. And so then this set is included in Kn, very good. And then the whole remark is that it contains all the extreme points. So the extreme points of Kn are the rank n orthogonal projections. Okay? And those guys are in that set because they come from Slater determinants, and they are exactly the gamma psi with psi of Slater, as you know. Okay, so now you have a convex set which is closed and which is included in another convex set, but it contains the extreme point of the bigger convex sets, and so they must be equal. Okay, so you have equality. So the full thing is, why are rank n orthogonal projections the extreme points of that set? This I leave as an exercise, it's not so difficult. But that's the way you should think about it. Somehow when you work with mixed states, what corresponds to Slater determinants, or namely these rank n projections, are exactly the extreme points of this convex set. Good. So now that I told you all this, we can start our study of the LDA for the kinetic energy T. Okay? And so let me remind, and I will only discuss fermions because for bosons we know what T is. So let me remind you that for fermions we know that T of rho controls the gradient square root rho squared, and I explained to you that one can prove that it's also less than a constant that depends on n, the gradient square root rho squared, but the constant is actually huge, it's like n squared or maybe n to the 2 of d. So this estimate is not so good, somehow it doesn't behave properly. So there is in fact the Liptian inequality, from 75, that states that there is a different lower bound that T of rho controls the integral of rho to the 1 plus 2 over d, where C is a universal constant that only depends on the dimension, and that's strictly positive. Okay? So it's a different lower bound than this one. And you have to realize that this lower bound behaves completely differently when you have a system that grows thermodynamically. I mean, if you have a system that's very big. So for instance, so example, let me think of having rho which is constant over a huge domain. Okay, so I take, if you like, a very large cube. and I have rho that's constant over that cube. Of course, square root rho has to be in H1, so I cannot take rho exactly, or I can take rho constant, but then I have to smoothly put it to 0 close to the boundary. Okay? Then you see that this lower bound actually behaves like the boundary, so it's a boundary term. Right? So you see that, so this is L, and you see that the boundary square root rho n, this behaves like L to the d minus 2, L to the d minus 1, if you like. So it's a boundary term. That also tells you, that this constant has to behave very badly, right? Because of course for such a rho, then n is like L to the d. Okay, so the constant here has to compensate this thing, but it actually blows up crazily. And if you look on the other hand as the lower bound of the Lithium inequality, then you see it behaves like the volume. So if you like, for fermions, in a thermodynamic regime, the kinetic energy behaves like the volume, which is very natural, and which is not captured at all by this, but very well captured by this. And so maybe a small exercise that we could do is to come up with an upper bound of semi-classical nature. Okay, so what would be the lowest kinetic energy that we can build for a rho that's constant? Okay, so let me do this. So let me take a huge cube, QL, that's minus L over 2, L over 2 to the power T. And then I want to take rho to be constant over this large cube. Okay? And of course, I can't quite do that because rho has to be in H1, and square root rho has to be in H1. So let me smear out with a given chi in this infinity compact support, integral chi is 1. Okay, should I do that? So I take rho constant over a huge cube, then I smoothly go to 0 close to the boundary, and then let me now construct for you an upper bound on T, so a trial state that will have a reasonably good energy in this, and which will be in a semi-classical regime. So what do I do? So I'm going to construct a Slater determinant, or if you like, gamma projection. And so I introduce a UK of X, which is this guy divided by L to the D square root. Okay? So that's the square root over M. Okay? And then I put a phase. I have to put a phase because I need the UKs to be orthogonal to each other. And the trick of this computation is that I can make the UKs orthogonal very easily by doing k dot x, where k is in the dual lattice 2 pi over L z. Okay, so I claim, so k is not, is a vector in the dual lattice 2 pi over L to the zd, and I claim that those UKs are orthogonal to each other. It's a small trick, it's a nice trick, very easy. So why? Because you see, if you compute UK prime, okay, so you get 1 over the volume, and then you get 1 QL star chi, and then e to the I k minus k prime dot L. So x dx. Okay? And now you see, it's a convolution. So what is that? So let's just 1 QL star chi, Fourier transform at k minus k prime up to a constant, and it's on 2 pi to something. And the whole point you see is that the Fourier transform of the convolution is the product, also to some 2 pi. But when you look at the Fourier transform of the characteristic function of a cube, if you evaluate it on the dual lattice, then you get 0. when k is different from k prime. So you see, it's a very easy way to create orthogonal functions of constant density, essentially. Okay, so now I take a Slater determinant with many k's, and then I compute the kinetic energy. So the kinetic energy, so you see I get an upper bound on T. So what is T? So T is going to be rho 0 okay, so I need that rho 0 is n over volume, where n is the number of functions I take. Okay, and then I get an upper bound on T, which is what? Which is, so you only have to compute the kinetic energy of those UKs. Of course, there will be a term when you take the gradient of this function, a term when you take the gradient of that function, and then you integrate. Okay? But this is the main term, so you will just very easily get the sum of the k squared plus a little rho of the volume, because when you take the gradient of that function, then it's a surface term. Okay, good. So now we see, now we want to make this very small. So you see what we have to do. We have to choose the k squared all different from one another, so that the sum is as small as possible. And we have to pick n of them, where n is rho 0 times the volume. So that's the picture you've seen many times, I suppose. So you have the lattice z to the d. So that's 2 pi over L z to the d. Okay? And here is 0. And so you have to fill this lattice with points, and you have to minimize this sum here. So what you do is you take the k's as small as you can, but they have to be different. So you start with the origin, and then you just go like this, and you fill them just to make sure that they are as small as possible. Okay? And then you have to know what's the typical, so that will form, you know, a kind of square or ball. Okay? So then you have to know what's the typical radius of this ball when you know that you put n points satisfying this relation. And this is all about Riemann sums. Okay? So you can compute the radius r in terms of rho 0. So how do? You just count the number of points in a ball. Okay? So the number of points in a ball is really L over 2 pi to the d times br. Okay, so that's the number of points, because my small cubes, they have that volume, 2 pi over L to the d. Okay? So the number of points is, so that's going to be the number of points in a ball of radius r. Okay? And this you want to be equal, or of the same order, if you like, as L to the d times rho 0, and so you find the formula that rho 0 has to be dr over 2 pi to the d. Or if you prefer, you find r in terms of rho 0. Okay, so that's the radius of the ball, which you have to fill completely, more or less, if you want to achieve a certain number of points per unit volume, which is the rho 0 you had fixed before. So you see, you get the formula that R, not the computation on the board, but I found 2 pi over B1 and the rho 0 to the 1 over T, and here is also 1 over T. Okay, so that's the link between the Fermi level and the Fermi momentum R in Fourier space that you need to impose to get the correct density when you fill the points starting from the center. Good. And now that you know what R must be, then you can compute how this sum behaves, because now it's a Riemann sum, right? So you will take k less than R with k in 2 pi to the L z to the d. And so because it's a Riemann sum, you deduce that this term behaves like L to the t divided by 2 pi to the t times the integral k less than r of k squared dk. And what's the conclusion? So the conclusion of this whole computation, which I'm sure you know and probably have done already, is the following. So we found an upper bound of the kinetic energy of a density that's very flat over a large cube, and then somehow goes smoothly to 0. So we find a certain constant, which is the Thomas Fermi constant, rho 0 to the 1 plus 2 over t times rho u plus little o of a plus t. Okay? And what is the Thomas Fermi constant? So you just have to compute this integral in terms of r, and then express r in terms of rho. And if I didn't mess up, I found 4 pi squared t over t plus 2, and then d1 to the minus 2 over t. Okay, so this is semi-classical analysis, right? So that's what you get. You see, you replaced everything by integrals in phase space, and so that's what you get. Oh, maybe I can keep this. No, maybe I don't. Okay, so now a natural question is very good, but is this the right behavior of the kinetic energy when rho is flat? Because somehow we believe semi-classical analysis tells us that it's probably true. And it turns out that this is exactly what LTA is. So LTA is what is telling you that if rho is very flat, then locally you can replace rho by essentially a constant, and then semi-classical analysis tells you that this must be the answer. So let me state a theorem that's valid for every rho, and not necessarily this constant rho. It's the following theorem, which says that for all rho non-negative with integral rho, well actually, integral rho integer, and rho in H1, then you have a bound, any dimension, which tells you that T of rho can be bounded by the Thomas Fermi constant times 1 plus epsilon rho 1 plus 2 over T, and then plus a constant over epsilon grad square, and then a lower one of the same kind, Thomas Fermi 1 minus epsilon rho 1 plus 2 over T, and then minus a constant over epsilon grad square root for square. And this is valid for every epsilon positive, so maybe between 0 and 1. So this theorem gives you universal bounds on the lowest kinetic energy of quantum states at a given rho. And these bounds, they are useful only when rho is very flat. Rho doesn't have to be exactly constant, or it could be very flat in some places and then very flat in other places, but with a different constant. Okay? And so when is this useful? You see, you have epsilon here and 1 over epsilon there. So this is useful when this is much smaller than that, because then you can optimize over epsilon if you like, and get something small. Okay, so this says that when this is much smaller than the Thomas Fermi energy, then T of rho really looks like the Thomas Fermi kinetic energy, the two leading order. Okay, so And that's LDA, and the spirit is the following. So you have a row, maybe it does this, maybe it does that, you see very flat, I don't know. So very flat or large domains, there might be some transition regions or whatever, we don't know. Then you see that as soon as the constants or almost constant parts are very big, then you can replace T by the Thomas Fermi approximation. Okay. References. So a bound of that form was first proved by March and Young in 1958. And that's only in one dimension, and they have a better bound, which gives the Thomas Fermi in 1D it's rho cube. Okay. And then they get plus, I think it's not 1/2, because probably they put the square root in it. Let me write the square root 4, but that's just rho prime in 1D. Okay, so you see, they proved exactly the same, except that they do not have an epsilon here, and here they have a fixed constant, which by the way is the optimal constant for the lower bound. Okay, so that's a very famous bound. And so it's an open problem to remove the epsilon in higher dimension. And I think it would be very interesting to have a similar bound with exactly Thomas Fermi and then a constant and no epsilon. But we don't know how to do. So we can get as close as we like to the Thomas Fermi constant, and then we pay 1/epsilon for this greater method. So then the first lower bound, so that's Marsh and Young. Then the first lower bound was proved by Nam. I think it's in 18. He only proved the lower bound, and he had minus constant over epsilon 3 plus 4. So that was a much worse lower bound, you see, in terms of epsilon. But that's the first time that there was a bound of that kind. Of course, the lower bound is more difficult in a way. To get an upper bound, you have to build a trial state. To get the lower bound, you have to find another argument. So then with Robert and Elliott in 19, so we proved the upper bound. The one with the C over epsilon, as was stated. And then there was a recent paper by Robert and Jan Philippe, who did the lower bound with minus constant over epsilon, so they corrected, if you like, the bad behavior of 9. So, one example of an application is when you have a row and you scale it to make it very slowly varying. Okay, so let me take a function over 1 in 1. Okay, maybe integral over 1 is 1. Simplify. Then I can scale my row 1. Okay, so let me introduce row n of x, which is just row 1 of n 1 over d times x. So I'm just scaling row 1 horizontally, like this. You see? Did I mess up? I think I messed up. Okay. And so the integral of rho n is n now, as it should be. And then so the result, you see, is telling us that the t of rho n has a leading term, which is c to the left, n equals to rho 1 to the 1 plus 2 over t, the scaling, okay? And then if you optimize over epsilon, you will find a big O of n1 minus 1 over t. Okay, so you see, that's an example of one density that varies very slowly, and for which you can prove you can prove that the very complicated lowest kinetic energy that simplifies and converges to the Thomas Fermi kinetic energy. Just one word about the proof. The proof is actually not so difficult. Once you find, last proof was kind of difficult, but we found a way around. And so so what's the idea? Of course, the idea also of this calculation over there is that if you look at the free Fermi gas, so let's say that it's that guy, which is translation invariant. Okay, so it's an operator that's translation invariant. It doesn't have a trace. The trace is infinite. It's an infinite Fermi gas. But nevertheless, it has a density that's a constant. Okay, and this guy has constant density. Rho that you can compute in terms of R as is written over there. And so that's just BR over 2 pi to the t. Okay? And so if I fix rho, maybe I call it rho 0 again, so if I fix rho 0, I can find R. So that I have an infinite guy of constant density, and it has a kinetic energy unit volume. That's exactly C, Tf, rho 0 to the 1 plus 2 Okay, so somehow we want to use the free Fermi gas as the main tool to construct a trial state for a general rho. So in our mind, somehow we think that we split spaces into boxes and we look whether rho is almost constant. If rho is almost constant, we take the free Fermi gas. But then the boxes, we don't know what's the size. And so what we did was rather to split rho vertically in a way. So as you do for Lebesgue integrals. Just looking at the set where rho is equal to some constant, and there put the free Fermi gas, if you like, on that set. Of course, you cannot do something too rough, because rho has to be in H1, and square root rho has to be in H1. So you have to regularize a little bit. And so I'm going to tell you the trial state that we took. And that's the following. So I'm just writing the formula. So we took the following gamma, which is the integral over 0 to infinity. So we integrate over all possible values of rho vertically. Then we look whether rho has the value t. Okay? So eta is going to be very picked at 1. So we want to know whether rho has the value t. Then we put the free Fermi gas here with R chosen so that the density is exactly t. So I think you have to put 4 pi squared t to the 2 over d. Oh, maybe 1 2 over d anyway, so that's the R. And then we put back the localization t over rho of x. Okay, so here we really think that we look whether rho has essentially the value t, put the free Fermi gas, localized there. And then to make everything work exactly, you have to put dt over t. Okay. So the claim, so that's a trial state, it's a little bit complicated. So you have to, so here you have the multiplication operator in Fourier, here you have 2 multiplication operators in X space. So the full thing is an operator over L2, and then you average over T. So the first remark is that the rho gamma is rho. Why is it so? Well, actually, when you compute rho gamma, you will find the integral 0 to t, and then when you have such an operator and you compute rho, you will actually get eta of t over rho of x times t, because this guy has density t, dt over t. Okay, this guy has density t, and you have dt over t, so these two simplify, and you see that this is rho by scaling times the integral of eta. And so if you assume that the integral of eta is 1, so I'm really thinking of eta very close to a delta at close to 1. Okay? crazy trial state has exactly density rho of x for every x. Okay? And of course, so there is a problem that you want, so this is a non-negative operator, but you want gamma to be less than 1. Okay? So if you just say that this guy is less than 1, so you find that gamma is less than the integral 0 to infinity, and then eta t over rho of x dt over t. Just by saying that the operator in the here is less than 1. And so here now you can scale out rho, but there's no rho remaining. And so this is just equal to the integral eta of t over t dt. And so you have the second constraint that the integral eta over t must be less than 1. Okay, so the picture is the following. Eta is very close to 1. Okay? Eta's integral equal to 1, a bit like a delta. But it must be a little bit on the right side, if you like, of 1 slightly, to make sure that this is less than 1. And that's okay. Good. And then when you compute the trace of minus Laplace gamma, you actually can make an exact computation, and you get the following that you just copy. I'm not going to do the calculation. So you find that actually the kinetic energy is really the Thomas Fermi energy times a constant, and the gradient term times a constant. And so what you do, you see, you want to make the first term very close to epsilon, which tells you that eta has to be concentrated very close to 1. Okay, but of course you pay for the second term because there you have eta prime. And when eta is very concentrated, of course, eta prime you pay. And so by optimizing over eta, you get the upper bound. Okay? I have to mention that here we really use the fact that we work with mixed states. Because we work with a little gamma, then we can come up with any crazy operator between 0 and 1. And so we have no clue, so open problem. I will do the same with pure states. Okay, so here we don't care about the big n-body state because we found the class of gammas and then we only work with a small gamma. We don't have to construct really the big gamma. We know it's a complex set, there's a way to find one big gamma, we don't care. So it's very easy in a way. But how do we know if this small gamma comes from upside? In general, we don't know. So there must be a way of attacking the problem directly with psi. Or maybe you could also ask, can we do it only with Slater? Because over there we only use Slaters. This is unknown. And we don't know how to. And then maybe one remark about the lower bound. And so Robert and Jan Philippe, they made the observation that you can, like for coherent states, you can actually look at the dual of what we've done here. So there's a way of thinking of this in the dual sense, in order to get lower bound a bit like coherent states. So look at the dual method, all right, it's a bit vague. A bit like for coherent states. I'm not going to tell you more. Okay, but I hope you are interested and look at the paper. Okay. Now I come to some of the main result, which is LDA for f of rho. So we've done LDA for T of rho, so we've explained, we found one regime in which T of rho simplifies and can actually be replaced by the Thomas Fermi kinetic energy as a function of rho. Now we ask if there is something similar for F, which now is an interactive problem, it's much more complicated. And so we will now be in dimension 3, and W of x will be the Coulomb. And in the quantum case, no other situation, well, essentially, well, actually, it's not quite true, but very few other situations have been considered. And on Friday, Peter will explain to you some results in the classical case. But today I'm in a quantum zero temperature. And so we want to do the similar case, similar situation. So we have a density rho. Here it is. And so we want to say that we will do as if rho was locally constant. So we think of splitting our space into boxes, if you like. And then we will replace rho by a constant locally. Okay? And then we will ignore the interactions between these boxes. And in each box, we have rho that's a constant of our box of a certain size. What we will use is just an infinite gas having this constant. So here you have rho of x, you are in the neighborhood of a point x. We will introduce an infinite gas that has constant density, and we will use the energy of this infinite gas locally. That's LDA. Exactly as we did with the free Fermi gas, whose where was it? Yeah. So the free Fermi gas is this gamma. Okay, so now we have to do the same, but with an interacting problem. So let me state the theorem. So again, so dimension 3, Coulomb, no speed, to simplify. So the theorem says the following. So it's a little bit the same as the other theorem, but now we need more on the right side, right? So we ask more. We're not going to put the assumptions on rho, because the assumptions are just the ones so that everything I write is well defined. So we compute the f of rho, and then I will write an absolute value instead of upper and lower bounds, because we both. And so we want to replace f by a local functional, okay? But it can't be quite right because Coulomb is long range, so it's clear it can't be completely local. And so the thing is that there will be the direct term, and then it's going to be local. So it's going to be local if you first subtract the direct term. So let me subtract the direct term, which is 1 half rho x rho 1. X minus 1 dx dy, and then there is a certain function f of rho of x dx, and the theorem says there exists an f, the way that f is defined comes from the inequality, such that you have this bound, and this is less than epsilon rho plus rho squared plus c over epsilon r squared rho squared. And then we have the worst crazy order estimate, square root rho to the 4th. Okay, so that's the bound. For all epsilon positive, you can take epsilon less than 1 if you like. And that's where f is a certain function from r plus to r. And instead of stating results, let me make a drawing about the f. So maybe I can just write where f is.
But f bar is just f, or?
Yeah, so there will be a comment soon. So you've seen that there's a bar here.
Yeah.
Good. Where f, okay, for R, where f, so let me write just is the energy, unit volume of an infinite gas of electrons with constant density. And that's of course with the direct term removed. theorem is valid for every row, but it's interesting when rho varies slowly, and if rho is constant over a huge cube, exactly as we did here, then the theorem tells you what F is. F must be, you see, the energy per unit volume, minus the direct term that goes up faster, okay, of an infinite gas, which has constant density rho. That's the idea. And let me now tell you what's known about F, and then I will make other comments about the theorem. So it's known, so I'm just drawing F. So this is F. Here is a 0, if you like, here is F of 0. Maybe I call it rho. Okay. So it's known that at the origin, F behaves like minus a constant, sorry, that's no integral, rho to the fourth term. Okay. This constant is strictly positive. Let me call it the Wigner constant, which I will discuss tomorrow. And then it's also known that at infinity, F behaves like the Thomas Fermi rho 5 term minus the Dirac rho 4 term. So the Thomas Fermi is the constant I introduced, and the Dirac, I think Ian Philippe mentioned it, at least, at infinity. And so it's known that this function has that shape. It's known that it's a continuous function, it's locally Lipschitz. Actually, it's believed that maybe it's not, it's not differentiable everywhere, so there might be some jump of the derivative at some places corresponding to phase transitions. Okay? And so the behavior at small density, the system is classical. And so you find some classical problem that I will discuss tomorrow. And at large densities, so the behavior I wrote here was actually proved, well, they did not consider the same model, but it's a consequence of their result. So this behavior was proved by Graf and Solovay. Was that in 94 or 95, something like that. And let me mention that there are some very famous conjectures or predictions about the next orders in rho. Okay, so it's believed that the next order is of the form A rho of rho plus B rho. And this is due to Gelman-Bruckner and Roman Pines. So there are many recent works studying infinite Fermi gases at high density. And that's somehow probably the most important Fermi gas, namely the Coulomb gas. And then at large densities, you have these high correlations which diverge. You see this log appearing. It's very complicated to prove anything. Good. F bar is not F. Where is the yeah. So there is a somewhat. We are a little bit ashamed that we did not manage to prove the theorem for F. So F bar is actually another function that's less than F. And so the theorem gives you actually a lower bound to the true F, but we could not do it for F. But we expect the same for F. Expect the same for F. And what is F bar? So F bar is the grand canonical version. Canonical version of F. So it's defined as the minimum, but instead of taking one big gamma, you take a family of gamma n of any number of particles. Okay, so you take a family gamma little n and infinite family of operators. Okay. Of mixed states, okay, each of them having living in the n particle sector. Then you sum the energies, the trace of Hn of 0 gamma n. Okay, so that's the average energy of my mixed. So we are doing a mixed state, but also with respect to the number of particles. And the sum of the trace of the gamma n is 1. And And of course, the rho of gamma, which is just the sum of the rho gamma n, must be 1. Okay, so it's a little bit the same as our f, but it's a kind of convexification with respect to the particle number. I think everybody, or actually we believe that the exact same theorem must be true for f, but it's always much easier to construct trial states when you have a lot of freedom, in particular when you can remove add particles and you don't have to worry how many particles you put, okay, for building trial states. Of course, for lower bounds, if you prove a lower bound for a much smaller or for a smaller functional, then it's a lower bound to the true functional. But it's a little bit a shame that we cannot construct n-particle mixed states having a fixed n easily to prove this theorem. We expect it's true, but it could be a little bit technical. And it might not be so easy to do. Okay? So that was the first remark. Then other remarks, so f is very important. The function f over there. And let me emphasize that this f is unknown. Right? It's the energy per unit volume of an infinite gas, infinite interacting Coulomb gas. It's not known. However, it's a function of one variable. So there are lots of numerical simulations as well as predictions. So what chemists and physicists do, they look at the behavior of F at low density, look at the behavior of F at high density, and then they did some very complicated Monte Carlo simulations for a few values of rho, and then they have some kind of interpolation to find some approximation of this function of one variable. Okay, so one of the most famous is the one by Claude and Wang from 92, sorry, 92, which is an approximation of f. So you don't know f, but people have approximations of this function f, which then they use. So now you end up with LDA. So what is LDA in Conshan DFT? What is LDA? Now you know what it is. Okay, so you will be solving the following minimization problem. So you write as En of V. You replace it, because now you do an approximation, by the minimum, maybe I should write infimum over the small gamma, okay, of the trace of minus Laplace plus V gamma plus the direct term 1/2 rho gamma of x, rho gamma of y, divided by x minus y, okay, and then plus the integral of the exchange correlation function dx, okay, where the fxc, maybe I call it e because before I had an e. So the efxc, the exc of rho. So let me remind you that here you have to put the difference. Okay, so what is exc of rho? So that's the f over there minus the t. Okay, so this is LDA. So when you run code like PySCF as I did on my computer and I displayed some results, when you type LDA, this is what it's doing with f, usually this parameterization here. So you see, it would be very interesting to better understand this difference here. Okay, so at large densities, this behaves like minus Dirac rho to the 4/3. At low density, this is negligible. It still behaves like minus rho 4/3 as well. Okay. And let me finish by mentioning that Anantaraman and Frances, it's not Nalini, it's actually the brother of Nalini, Arnaud, in 2009. So they proved that this problem has minimizers, except, I mean, of course, we don't know F very well, so they've put some assumptions on that E. So existence of minimizers they have a bunch of assumptions which I think are true for the true EXC, but they assume it's decreasing. I don't think it's known if it's decreasing. But they claim that all the parametrizations used in practice are decreasing, so maybe it is decreasing, I don't know. Nobody knows. And then actually in 11, I also proved existence, except I proved existence plus the fact that your Slater determinant if the EXC is concave. When I say existence, I mean it depends on your V, of course. So existence, you look at the case of a molecule. Okay, so V is the V generated by a few nuclei, and you assume that N is less or equal than the total charge of your nuclei, and then you can prove existence of minimizers for this problem. And then let me finish with just one remark and I'm done. Tomorrow, we will discuss the constant CW here, CW, and there is a famous conjecture which is due to Wigner, and which was actually mentioned yesterday by Aspian, that CW is somehow confused with a minus, but must be minus zeta of 1 for the BCC. Okay, so you remember what Aspian told you? Well, I will re-explain tomorrow. But when you have a lattice L, you can introduce an associated zeta function, which is just the sum with the 1/2, the sum with the z in your lattice belong to 0, 1 over z to the s. Okay, so it's a generalization of the Riemann zeta for general lattice in any dimension. And this sum converges when the real part of S is strictly larger than D. But like for the Riemann zeta, there is a meromorphic continuation to the whole plane, except for D. Okay, so actually there's an extension to a C minus D, meromorphic. Okay, and then I can compute in dimension 3 the value at 1 for the BCC lattice. So BCC is when you take the cubic lattice and you put one point in the middle of every cube. Okay, and the conjecture is that this constant is given by this, which is about 1.44. It's a famous conjecture, nobody knows how to solve this conjecture, and maybe I'll talk a little bit about it tomorrow. Now I have to stop, and thank you for your attention. Very good question. So GGA is when you put gradient corrections, and so the whole game would be to go one step further in everything I told you. Okay? For F, it looks extremely complicated, but for T, actually, I had a remark which I skipped because I was a bit late, so let me make it. Thank you. Where should I put it? Here, maybe remark. So there is a conjecture, or maybe here. Right? So here you see, you take a row, you scale it, then the leading term is this term here. And so there is a conjecture for the next order term. And it's very clear what the conjecture must be. We don't know how to prove, but then the value of the next order term, which is a gradient term, is used in all the GGAs. And what is the next order? So let me write it here. So next order conjecture are predicted to be. Now we mess up the constants, so it's d minus 2 divided by 3d, and then r squared. Okay, so in particular, you see that this n 1 minus 1 over d is not optimal. You think it must be a 2 over d, not 1 over d, because you have a gradient square. Okay? And then the constant must be this. This is what semi-classics predicts. Okay? And if you like, it's the dual to go in semi-classics with a potential v to, with two orders, with two terms. It's very important that this has a sign, because you see that in dimension 1 it's negative. And this is one of the reasons why the free Fermi gas is not optimal for the Liptirian inequality in one dimension. That's one way of proving it, if you like, except we don't have this result yet. But, so the fact that it's negative is due to some instability of the free Fermi gas in one dimension. And the fact that it's positive in higher dimension goes in favor of the famous Liptirian conjecture concerning the value of the best Liptirian constant. Okay, so for the kinetic energy, that's the prediction. You could write a conjecture, for instance, for such rows. And for F, so there are predictions for the values of the gradients as well, by chemists and physicists, which they use in their function also in the GGAs. But it sounds very hard to prove anything.
More questions? Yes?
So in the theorem, is it necessary that the integral of rho is natural number or just finite?
Here, no. Right. So here, actually, you can remove this. I was hesitating when I stated the theorem because so far I did not speak about rank. I had not spoken about rank canonical states. So of course, when the integral is not an integer, it means you have to look at the rank canonical state. But actually, the proof works. So this you can remove. So of course, then it means your t has to be. You have to know that when it's not an integer, then you have to use a rank canonical state instead of using a canonical state. But that's correct. Yes. So if you like, the t bar is equal to t.
Maybe one more question. So you mentioned the shape of f, and it's expected to have some sort of discontinuities of the derivatives related to phase transitions.
Yes.
Can you elaborate on that?
Well, I mean, it's a quantum system. Okay, so when rho is very small, it behaves like a classical system, and we are at zero temperature. The conjecture is that at zero temperature, it's always a solid, and solid means it's periodic. Okay. And on the other hand, at large density, it's really you really see the quantum nature. So maybe one way of looking at the problem, you see we have the kinetic energy and then we have the Coulomb term, and they don't scale the same. Okay, so at low density, Coulomb is winning, so the kinetic energy becomes negligible, we get a purely classical problem. And then at very large density, it's the kinetic energy that's winning, which is why you get the rho 5/3 leading order. And so if you like, at large density, you get a quantum fluid. And the free Fermi gas is a fluid. So so it's believed that there is at least one transition from solid to fluid. Of course, there might be many more transitions because it's not clear that it will be the BCC. So the conjecture is that it has the BCC symmetry for small rho. There could be transitions that you would get other kinds of lattices. And actually, if you put spin, it's even more complicated because you could also be ferromagnetic or paramagnetic. And there are actually some disputes at the moment whether if you put spin, there are more transitions or not. It's completely unclear. But if you do not put spin, then we actually have less numerical predictions because, of course, electrons have spin. So then it's a bit unclear. So I would believe that there is only one transition that corresponds to going from BCC to fluid. But it's just faith.
Okay, so if there's no further question, then let's thank Mathieu.